All right, congratulations to making it to the last day. It's an intense 3 weeks. Um, I don't know if I'm allowed to say this. You guys have been great. I've rarely given lectures with people who ask as many questions, which is excellent. So feel good about yourselves. Um, all right, so I will tell you a tiny bit left on supergravity theories, and then the rest of the lecture I'll try and tell you some things about supersymmetric backgrounds. We don't have lots of time, so I'll be a little bit I'll be a little bit compressed in what I tell you, but hopefully it will give you some idea. So just to finish off, last time we looked at the 8 supercharge theories. And we had things like, for example, in d equals 5, we had something called a very special real geometry times some quaternionic Kähler geometry. So these can again always be thought about, I don't like this joke, these can all be thought about in terms of G structures. And say in d equals 4, we had some special Kähler geometry times some quaternionic Kähler geometry. So these were the geometries of the scalar field spaces. Let me just tell you, these are all have this property that they're all defined on, they're all sort of defined using cones, or that's one way to think about them, in the same way that the Kähler-Hodge structure was defined via a cone. So let me just tell you a tiny bit about quaternionic Kähler. So quaternionic Kähler, it's sort of like Kähler geometry as a complex geometry. Quaternionic Kähler geometry or hyperkähler geometry wants to have quaternions as the coordinates. You can't actually do it, but that's what it's sort of trying to do. So this is actually the same as a torsion-free, let me write SP1 times SPn structure inside GL4NR. So these SP groups are the groups that preserve the norm on quaternions. Physicists sometimes write this as USP2 times USP2n, and USP2 is actually just the same as SU2. They're just isomorphic to each other. This USP, these are matrices that are both unitary and symplectic. So that's one way to think about it. Another way to think about it is that you can take, or alternatively, you can take a kind of quaternionic cone. So this is the space X over X. So that's something like, so before we had something like R squared, and here I had d psi plus A squared, right? Let me just call this whole thing some sigma 1 squared. And then I can have a sigma 2 squared and a sigma 3 squared. And then I have an R squared. And then here I have the metric on X. So whereas before, for a complex clone, we introduced coordinates. We had some coordinate u, which looked like r e to the I phi, and I could think of it as u1 plus I u2. Now I have a sort of quaternionic coordinate, which looks like u0 plus I u1 plus j u2 plus k u3. And there's an overall r, which is u0 squared plus u1 squared plus u2 squared plus u3 squared. And then there's some angles, and the angles are going in here. But they're all going to be somehow in the same way as before. We had sigma look like d psi plus A with some connection. There'll also be some connection pieces here. Okay, so I'm just giving you a flavor for how it works. And this cone, the cone, so if the cone is hyperkähler, that's equivalent to X being quaternionic Kähler. So in the same way for the Kähler-Hodge things, if the cone was Kähler, then the base was Kähler-Hodge. Now if the cone is hyperkähler, the base is quaternionic Kähler. And what do I mean by hyperkähler? Hyperkähler is the same as a torsion-free SPN structure inside GL4NR. So, and that can be defined by having three symplectic forms. Omega 1, omega 2, omega 3, and they all have to be closed. So I'm just giving you some information. That's what the structure is like. So if you have these three symplectic forms, it's preserved by this group. And here in this cone, right, n prime is going to be n plus 1 because the cone has 4 extra dimensions above the base space X. Okay. And then the other thing I just wanted to mention was just so we touch base with some theories you know. So we had the D equals 11 theory, and that had in it the bosonic fields were a metric and a 3-form. And then we also had some gravitino. In D equals 10, we had the 1-0 theory, and that has in it a metric, a B field, a dilaton, and then it also has a gravitino, and it has another thing which is called a dilatino, which is just a spinor half. And these hopefully are a little bit familiar from string theory, right? When you did this, when you quantized the string, the lowest energy modes in the superstring or in the zero energy modes in the bosonic string were a metric, a 2-form, and a scalar. So you see the massless fields of string theory appear. And if you do the superstring, you get these things as well. And then there was, so this is something like the, this is, if you add engaged fields, this would be like the heterotic string theory. So this is the low energy limit of the heterotic string theory. If I do the n equals 1, 1, you have these same fields. So we have GMN, BMN, phi, and then I get two different spinors. The plus and minus are telling you their chirality. I get two different dilatini, and then I also get some extra fields, CM, CMNP, which are like Ramond-Ramond fields. So these things are the Never-Schwarz fields. And I don't know when they did this, when Mariana did the superstring, if she talked a bit about that or not. So this is the low energy theory of type 2A string. And these things are potentials. So in the same way here, I had a field strength, which was dA. Here I have a field strength H, which is dB. And again, I'm going to have field strengths for each of these potentials. And they're not totally straightforward. They have Chern-Simons-like terms as well. They're more complicated. And then finally, for the 201, I get the same fields again. Now I get two fields of the same chirality. So now the fermions have the same chirality. I get two of them with both with plus and two here both with minus. And then now I get a C0, a CMN, and a CMNPQ. And this is, I'll write a plus there because it has a strange property that if I make the field strength F5, which is D of C plus, this has the property that F5 is equal to F5 star. It's self-dual if I'm using the Hodge duality, epsilon tensor, and 10 dimensions. And this is the 2B string, the low energy limit of the 2B string. Yeah. Why do I put this plus? just to say that there's a plus sign here in the self-duality. I might have muddled my conventions, but let's hope that that's reasonable. It's correlated with the way you choose the chirality of these spinors. So whatever the chirality of these spinors has to match with that, otherwise it won't be supersymmetric. Yeah. Okay, so that's my summary of supergravity theories. I realize maybe I should say to you, maybe I should have said right at the beginning, why should you care about any of this? This is a good reason you should care about it. So let me say, first of all, so why supergravity? So from one point of view, they're just interesting theories in their own right. So in particular, it's hard to couple higher spin to gravity. So even if you just asked yourself, I have a spin 3/2 particle and I want to somehow couple it to gravity, you're going to be forced into supersymmetry. So spin 3/2 plus spin 2 kind of forces you into supergravity. And the other interesting thing is that they're unique theories with, if you have enough supersymmetry. So that's always interesting, right? If there's somehow something that's kind of a unique theory. This is this old problem about thinking about quantum gravity in some sense, which I think I've mentioned a few times before. We really know that gravity is not UV complete. There should be some UV completion. If you're a negative person, you say there's no point in thinking about the UV completion because there'll be 1,000 different possible UV completions. You'll have one, you'll have one, you'll have one. We'll never know which is the right one. But as it is, we find it very hard to find UV completions of gravity. So I would say we know string theory is a UV completion. I'm not really sure we know any other things that are UV completions. So one possibility is that we're just really bad at finding UV completions, and tomorrow we're going to find that there are 10,000 of them. The other possibility is that somehow coupling to gravity is hard, and making consistent quantum theories of gravity is hard, and that's got to somehow have an assumption that there's something unique about gravity. So if you start seeing unique theories, or theories that are sort of on the boundary of what you can do, that's an interesting thing, right? So I think people may have different philosophies, but I think if you're thinking about quantum theory of gravity, you probably have to believe that there's something very special about gravity compared with other effective theories. Otherwise, you're kind of on a wild goose chase. You'll never know which is the right completion. And then the other reason is just that, as I said, that the low energy theories, low energy limits of string theory. So this has lots of practical kind of applications. So this is, they appear in like, so the sort of, they give you the majority of examples of ADS CFT. So most of those are the original examples, and most of them are like supersymmetric ones, right, that appear in supergravity. If you want to do any string phenomenology or cosmology, these are going to be the things you'll start looking at, right? You want to think about, at least to start with, what the low energy theories are. So, yeah. And as I said, originally people thought that they were going to be the full theories of full theories of the standard model, the right completion of the standard model. There is also a sense in which I told you it's hard to couple spin 3/2 or higher things to gravity. So if you're a real stringy person, you might say the reason these theories exist is because they're low energy limits of string theory. Right? A priori, there was no reason that you were going to be able to write down some local theory of supersymmetry. You have the global theory, but there's no reason that you could write down the local one. It turns out you can. And the other thing I want to stress is that I told you a very basic way of thinking about the supergravity. I just introduced the fields, I told you the action, and I told you what the supersymmetry transformations were. There's a whole load of literature, huge literature, on how do you construct those theories? How did you get there, right? And originally, people were very powerful, and they started just constructing them and trying to make the terms work. And then you start seeing more systematic ways of doing it, like doing superspace. But there are many different ways of trying to do those constructions, and I've only told you a tiny bit about it, all right? So there's a huge literature out there about how you construct the theories. Okay, so motivated by this thing, something you might in particular be interested in is particular solutions of the supergravity theory that preserve some number of supersymmetries. So that's the analog of having a solution of Einstein's theory that preserves some isometries. So for example, a black hole solution, right, has rotational symmetry, and it has time translational symmetry, right? So you can have a similar thing, but rather than translations in time or rotations, it's now super translations, supersymmetry transformations that are preserved. And that's something that we do all the time, because typically we want to do compactifications from 10 dimensions down to 4, and we might want to preserve some number of supersymmetries. Yeah. Yeah. Yep. Yes. Brilliant, excellent question. So from the supergravity classical point of view, you can put any gauge group you want. But the moment you say, it's a quantum theory and I need to cancel anomalies, I need to have no quantum anomalies for the gauge symmetry, or also for the local Lorentz symmetry, that restricts the gauge groups to those two things. That's this beautiful Green-Schwarz calculation. Yeah. Okay, so let me tell you a little bit about supersymmetric backgrounds. And let me start by telling you about the fluxless backgrounds. Okay. So, what do we want to look at for a supersymmetric background? So for a supersymmetric background, what I want to do is I want to set all the fermions to 0. And I want to look at a configuration of bosonic fields such that when I do the variation of the fermions, I get 0, and when I do the variation of the bosons, I get 0 for some epsilon. That's what I mean by a supersymmetric background. So if I did if I had a killing vector, I would have a background where there was some diffeomorphism, some killing vector, where if I did the variation of the fields, I got 0. Now the second condition, if you remember, the variation of the bosons looks like the fermions. And I set the fermions to 0 in the background, so this is automatically 0. So really, this is the equation you need to check for a supersymmetric background. Is that okay? Yeah. Yep. Right, so I want to look at a solution where all the fermion fields are turned off, and then I want to do a transformation on that solution, and it should remain the same. So in doing the supersymmetry transformation, it might turn on some of the fermionic fields. So I need to make sure that that background doesn't turn on any of the fermionic fields when I do the variation. Yeah, so this would be the fermions that I get turned on. Yeah. Are there any other questions? Yeah. Say that it's supersymmetric in the sense that it doesn't change the solution. So that's tricky because, for example, we can't set the metric to 0. We could set it to flat space, but we can't totally turn it off. Also, I'm looking at like kind of classical configurations. That's the idea. And like, you know, fermions have Fermi statistics, so I can't look at nice coherence of fermions. Whereas bosons have Bose statistics, and I can have like a big turned on boson background. So generally, you should think of this as, yeah, if I want to do it classically, I better turn off the Fermi fields. Is that right? All right, so in general, we're going to have some variation of the gravitino field. And that always looks like some Levi-Civita derivative on the spinor, plus more stuff, and plus things. So I wrote down some of these variations before. And in general, the things that appear here, so if we're doing, say, d equals 10 or d equals 11, the things that appear there are fluxes. And by that, what I mean is like things like f is dA in d equals 11, or h is dB in d equals 10, etc. Or it might be something like the dilaton, the derivative of the dilaton. So all of these theories have these flux degrees of freedom, which are like generalizations of electromagnetic flux, and they all produce corrections to the supersymmetry variation. Okay? So if I turn off the fluxes, so if all the fluxes are 0, then I'm just left with this equation. And the only boson and the background is pure gravity. So the bosonic background just is some metric, because I've turned off all the other bosonic degrees of freedom. But I can think of this, but this is just a torsion-free G structure. So how do I think about that? So think about my invariant objects as being the pair, which is the metric, and this epsilon, which is a solution to this equation. Right? This thing is some solution to the equation that is 0. Yeah. Only fluxes? Well, one thing is just to look at each of the theories, and you look at the variations, and you find that that's the form it takes. From the other point of view, if I've turned off all the other degrees of freedom, I've only got the metric. So whatever the corrections are here, it's going to be something I could construct with the metric. And the only other things are curvatures, and they have too many derivatives in them to close the supersymmetry algebra properly. So that's kind of all I could have written down in some sense. Yeah. And actually, in any supergravity theory, if you turn off all the degrees of freedom except the metric, it will have that form. Okay. So if you think about this, the GMN, this is an OD structure, or maybe a OD minus 1 structure, if I'm in and then the epsilon, this transforms under spin D, and it will be invariant under some subgroup G that lives inside spin D. Right? If I have a particular epsilon, there'll be part of the spin group that leaves it invariant. So this is actually just equivalent to a G structure where G is some subgroup of spin D, or if you want, spin D minus 1, depending which signature I'm doing. Okay, so let's do this in a bit more. And then, okay, so that means it's a structure, but in addition, we have by construction, this is the Levi-Civita, so by construction, this thing is 0, and this thing is 0, so that means it's torsion-free. Right? Because the Levi-Civita connection is a torsion-free connection, so I have a torsion-free connection that's compatible, so that means it's a torsion-free structure. Does that make sense? Or are you all too exhausted? Okay. So let's think about how we actually do this. So let's do an example. So suppose I want to take D equals 11 and go down to D equals 4 flat space. So suppose I want to compactify D equals 11 down to D equals 4. So I would choose my 11-dimensional metric to look something like, this is the flat metric. And I want to choose my 11D space to be a product of flat space with some internal space, and this is going to be 7-dimensional. Right? And my metric's going to be a flat metric there, and then some metric on the 7-dimensional space. And let's turn, and I'm going to take F is dA, and I'll just set it to 0, so there's fluxless. Now, I really want to analyze things on this space, so I do some Clifford algebra, so I do some spinor stuff. So I do a spinor decomposition. So I can take my spinor in 11 dimensions, and I can think of it as a product. So I can think of it as chi tensor eta, and chi is going to be something that corresponds to the even Clifford algebra in 3.1, and eta is going to be something that corresponds to the even Clifford algebra in 7.0. Okay? So I just do a decomposition like that. And then in 4D, we just get that the derivative of chi has to be 0. So that just means chi. And then in 7D, because there we just got flat space in 4D, right? And then in 7D, we get the Levi-Civita connection on eta. has to be 0. So this is the equation. This is sometimes called the killing spinor equation. So it's like a killing vector, but it's now for a spinor. Okay, so what's the structure? So all I'm saying here is I did it in general, but now I'm saying, okay, actually, if we focus down a little bit and we're actually doing a compactification, we're not really interested in this equation in the full 11-dimensional space. It just becomes an equation on the 7-dimensional space. Does that make sense? So now we have this pair. So we have the pair G, Mn, and eta in 7D. And the question is, and so actually the even Clifford algebra in 7 dimensions looks something like M8R, if I remember correctly. So the spinors have 8 components. So now the question is, so if I have a spinor, so if I have a particular spinor that might look something like 1, or might look like something A, 0, 0, 0, zeros everywhere else, right? So just turn on some spinor. What subgroup of spin 7 leaves eta invariant? That's going to be what our G structure is, right? And the answer is the following. The answer is that G is this group G2. So this is an exceptional Lie group. So the pair GMN, which is and indeed this is a subgroup of SO7. We thought of it as a subgroup of spin 7, but it turns out it's actually a subgroup of SO7. So this pair is equivalent to a G2 structure. Yeah. Sorry, it's zeros all the way down. So I just fixed some, I mean, you could fix anything you want, but why don't I fix one with something in the first component? Yeah. So something and then zeros everywhere. Yeah. Yeah, sorry. But this is a slightly complicated way of defining this structure. So this is actually equivalent to the existence of a particular three form on M7. So let me tell you what that three form looks like. So that three form, I'll call it phi, can be written in the following way. So given a frame, I can write it as E124 plus E235, plus I'll tell you what this is in a moment, plus E346 plus E457 plus E561 plus E672 plus E713, where given a frame, given an orthonormal frame, A. This thing EABC just means EA, wedge EB, wedge EC. Or equivalently, this is just 3 factorial times EA, M, EBN, ECP, anti-symmetrized. So this is a particular 3-form. It's not a general 3-form. And it turns out that if I have a 3-form of that type, it's invariant under the group G2. So an equivalent way of defining this structure is either as the pair metric and spinor, or better as a 3-form. So this is very like for the Kähler thing, right? I had a 2-form and a complex structure. To define this thing, I just need this 3-form to define a G2 structure. And then torsion-free tells me that the form is closed, and it's also co-closed. So because G2 is a subgroup of SO7, this guy actually defines a metric in a complicated way. And so I can take the Hodge dual, and torsion-free means that it's both closed and co-closed. Yeah?
We have an action to start which involves the bosons of fermions.
Yes.
If we are imposing that delta epsilon of the fermion is equal to 0,
Yeah.
and delta epsilon of the boson is equal to 0,
Yes.
that epsilon would be a symmetry of the whole action, right?
Yes.
New symmetry.
So it's a symmetry of the background. So I'm choosing a particular background, a particular configuration of fermions and bosons, and it's a symmetry of that particular background. It's not a symmetry of all backgrounds. Yeah, yeah. Same way like a black hole has certain symmetries, but a general solution of GR does not have those symmetries. Yeah.
But it would be a new kind of symmetry, right? Because the entire action is invariant.
So don't think of it as an invariance of the action. Think of it as a symmetry of a particular solution of the action. Yeah, yeah. So this is what's called a G2 manifold, or sometimes called a Joyce manifold, because Dominic Joyce was the person who really started constructing examples of these manifolds. I can't help but tell you something kind of cool about these numbers. You might wonder where these numbers come from. So yeah. Yeah, so you can see that you could put these conditions on some manifold. The question is, are there any solutions to that? And that's a hard question. And so there were some fairly trivial examples. And then Joyce came up with a way of constructing relatively large families of examples. So there's a background mathematical question, which is how do you show that there are families? How many actual Joyce manifolds are there? How many different manifolds can I find that satisfy these equations? And unlike the case of Calabi-Yau manifolds, where we have powerful theorems that say they exist given certain topological constraints, we don't have those theorems for Joyce manifolds. Yeah. So if you're wondering where these numbers come from, you can do the following. So I write 1, 2, 3, 4, 5, 6, 7. And I can do a step where I start with any one of them, and I jump by 1, and then I jump by 2, and then I come back to where I started from. So that's 1, 2, 4. So that's the 1, 2, 4. And then if I did the next one, I would start at 2 and go to 3 and then jump to 5. That's the 2, 3, 5. That's 2, 3, 5. And that's where those numbers are coming from. And if you want to know what they're related to, we talked about complex number, real numbers, complex numbers, quaternions, and there's these weird things called the octonions. So there my number is something like Z0 plus Z1 E1 plus Z2 E2. Maybe I should call this something else. I1, ooh, that's terrible. Let me call it K1, K2, plus all the way up to Z7, K7. And these things are like I, J, and K. So these all have the property that K, let me write 1 there. K1 squared is -1, K2 squared is -1, etc. They look like the square roots of -1. And then I also have a property that if I do Ki times Kj, it's some number phi ijk times Kk. So if this was quaternions, this would be I times j as k. Now I have to give a thing for 7 things. These numbers are these numbers. So the numbers that are appearing here are the ways that tell you how to multiply octonions. So put another way, the G2 group is the automorphism group of the octonion multiplication. And that's what happens with the exceptional groups. For each exceptional group, there's a kind of complicated way of defining them using the octonions. So in some sense, they're wanting to be groups associated with the octonions. Okay, so that was one example. So I can then just give you a table for what happens if I do the same thing in other numbers of dimensions. So we then have a set of basic examples, basic cases. So let's do the dimension D. Let's have the number of killing spinners. So that's the number of solutions to the equation. That's 0. That could have more than one solution. And then I'll tell you what the structure group is. And so if I'm in 4 dimensions and I have one solution, the structure group is SU2, which is the same thing as SP1. And this is a Calabi-Yau twofold. Or it's sometimes also, if it's compact, it's also sometimes called the space K3. Yeah? Why can't you go to something with 6 things or 7? Yeah, okay. So what you require is that it's a division algebra. So you can like add, subtract, multiply, and divide. And it turns out they're classified and there is nothing in between. Yep. It's closely related to another problem, which is you take a sphere and you ask, when is it parallelizable? When can I introduce a global set, a global frame on the sphere? And the spheres that are parallelizable are S1, S3, and S7. And if you add 1 to that, it's 2, 4, and 8. And they're parallelizable because of the existence of those algebras. That's a way of thinking about the parallelization. Yeah. Okay, so then I could do 6 dimensions with 1 killing spinner, and then I get the group SU3 as the structure group. This is a Calabi-Yau threefold. The 3 refers to the complex dimension of the manifold, right? So 4 real dimensions is 2 complex dimensions. Then I can go to 7 and 1 killing spinner, and That's this G2 manifold, and this is a Joyce manifold. I can go to 8, and now I have a number of different options. So I can have 1. That actually gives something with a spin 7 subgroup inside spin 8. That's sometimes called a Cayley manifold. I can have 2 solutions. That gives me SU4, and that's a Calabi-Yau fourfold. And then I can also have 3 solutions, and that gives me SP2, which is hyperkähler. This one's also hyperkähler, so it's very degenerate in 4 dimensions. Calabi-Yau and hyperkähler become the same. Okay, so those are the basic examples. And yeah.
When you say that in 4 dimensions, the Calabi-Yau and the hyperkähler are similar, you're saying that they have the same exact structure?
The same structure group. So they're actually literally the same thing. So because SU2, there's an accidental isomorphism between SU2 and SP1, defining it as a Calabi-Yau background or defining it as a hyperkähler background, you get the same thing.
Also, if it's compactified, so you have a K3 with
so if you want to do it on a compact space, then for the hyperkähler manifolds, basically all you can do is K3. That's the only compact 4-dimensional hyperkähler manifold. Yeah, was that the question? Yeah. Yeah.
So then, connected to the condition for transformation, so if you have closed, that means that phi is not a harmonic freeform, right? So isn't the condition for this for M7 just to have the cohomology?
It's more than that, because you have to be that cohomology group has to admit a harmonic form which takes exactly this structure. It's not a general harmonic form. Yep. Okay, so let me just say a little bit more and then we'll take a little break. So for the Calabi-Yau manifolds, so an SUN structure inside GL2NR, this is equivalent to a 2 form, which is like a Kähler form, and an N form, which is a complex, so a complex N form, which is sometimes called the sometimes called the holomorphic N form, and torsion free tells you that these are both closed. So we did Kähler before, and we had a symplectic form and a complex structure. When you go to Calabi-Yau, you can absorb you just actually have something which is a complex N form, so that's half of the top dimension, and that actually defines a complex structure for you. Okay. If we have hyperkähler, so that's some SPN inside GL4NR. I think, as I said, that's equivalent to defining three 2 forms, omega I is 1, 2, and 3, and you just need torsion free, tells you that they're all closed. Just like here, you had to choose a special 3 form, it couldn't be any 3 form. Here, you can't just choose any 2 form and any complex 3 form. There's some compatibility between them so that they really define an SUN structure. So I'm not telling you that. And similarly here, there's some compatibility between the forms. And then just for completeness, there was also this spin 7. So for Cayley, we have some spin 7 structure inside SO8, and that's equivalent to defining some 4 form psi, and again the integrability tells you that it's both closed and co-closed. And then finally, those are the basic building blocks. And then finally, you can do more. You can combine things, combine the basic blocks. So that, for example, well, I guess I should also say, sorry, in any dimension, you can also do, so I have D, so this is any dimension D. The number of supersymmetries is just equal to the dimension of the spinner. And the G group is just the trivial group. So this is like a torus compactification. So if I compactify on a torus, I preserve all the supersymmetries. That's a sort of trivial one, right? And then I can combine things. So for example, in D equals 8, I could also have SU2 times SU2 as my structure. And that would look like something where the 8-dimensional manifold looked like K3 times K3. I could just take 2 combinations of the other one, right? Or in D equals 7, I could take the manifold to be S1 times M6, and then I would just have an SU3 structure, which just lives on the M6. So this would be like Calabi-Yau times a circle. So that's the full set of things you can build, right? You can build them out of those things. All right, do you want to take a break for 10 minutes? And then I'll tell you about what happens when you turn on the flux. Okay. Okay. So let me just tell you 2 things. So if I have a torsion-free G structure, then that actually, and G is a subgroup of OD, then that tells me that the holonomy of the Levi-Civita connection must live in a group G. So either you know about holonomy or you don't. The idea of holonomy is I look at loops in my space-time. I start with a vector there. I parallel transport it round. It could come back rotated. The holonomy group keeps track of all the ways it could rotate. So an equivalent way of looking at some of those structures that we talked about is that they're special holonomy. So the SUSY backgrounds correspond to some, or imply some kind of special holonomy. That means that the holonomy group is smaller than it needs to be. And it's not every special holonomy background, because there are other special holonomies like Kähler manifolds, which are special holonomy, but they don't preserve a spinner. Okay, so not every special holonomy background is a SUSY background, but every SUSY background is a special holonomy background. And also, every SUSY background are Ricci flat. So the Ricci tensor is always 0. And you can prove that provided that's, I'm assuming that they're Riemannian. And not, sorry, that they're not Lorentz. So this condition, you have to work a little harder if you're allowing supersymmetries that involve the time direction, but I sort of ignored that, okay? All right, so what about when you turn on fluxes? So, sorry, I wrote 4 before, but we're actually in section 5. Backgrounds with flux. So let's do an example. So let's do the example of type 1. And what I have then is I have a variation of the gravitino, and it's positive chirality. So this is in d equals 10. It's got positive chirality, and it looks like Levi-Civita. And then it gets an extra term, which actually looks like a torsion term, MNP gamma NP, acting on my spinner. And there's a variation of the dilatino. I'm actually writing this as in a slightly non-conventional way, so you might not see the equation like this normally, but it's useful for me to write it like this. And this has something that looks like, depends on the flux, and it also gets a term that depends on the dilaton. So here we have the fields G, Mn, Bmn, and phi, and my H is dB. That's the three-form field strength for B. Okay, so we need to set these things to 0. And we might again do some what I can do is I can take these bits and think of them on the other side. So this roughly corresponds to saying something like the Levi-Civita derivative of epsilon looks something like flux acting on epsilon, right, if I take it on the other side. But we still have the pair GMN epsilon, so we should still have some G structure. Right, because they're going to be invariant under some group, just as before. But what's going to happen is it's no longer torsion free because of this right-hand side. But it's no longer torsion free because the Levi-Civita, this thing is no longer 0, right? I can think of that in different ways. The Levi-Civita is no longer compatible, but the Levi-Civita is torsion-free, so I can always find another compatible connection, but that's not going to be torsion-free. So another way of saying it is that this connection is compatible, or equivalently, this connection is compatible, but not torsion-free. So I could either think of this connection, those two statements become the same because the group is a subgroup of G. But basically I have something that's no longer torsion-free. So I can still sort of do the analysis. So roughly speaking, what happens is that there's a notion of something called the intrinsic torsion. That's equal to the part of the torsion that's independent of the choice of compatible connection. So think of choosing all the compatible connections you can. For a torsion-free structure, you have to find one that has vanishing torsion. In general, as you move over all the possible connections, you change the torsion, but there might be a bit of the torsion you can't get rid of, whatever connection you choose. That's called the intrinsic torsion. And what's happening here is in the flux backgrounds, you basically get the intrinsic torsion gets related to the flux. So you can still characterize these backgrounds using G structures, but it's much less elegant. They're no longer torsion-free. Instead, they have some torsion, and that torsion's controlled by the flux. Yes?
Why is this well defined, the intrinsic torsion?
So there's a sort of picture. So let me just draw the picture. So here's the space of torsions, right? So this is some Tm, these are some sections of Tm tensor wedge 2 T star M. That's what the torsion looks like, some Tm MP. Here's 0. And then here, these are the torsions of a connection where this is compatible. And I might have one connection there, I might have a different compatible connection there. But moving along compatible connections, I can't reach the 0. So the intrinsic torsion is this much. It's the bit of the torsion I can't get rid of by changing my compatible connection. And then any two compatible connections will be related by some K, and this is a tensor. So the intrinsic torsion is really the image of this, you take the image of this K, and then it's the whole space T modded out by the image of this K, and that's what this intrinsic bit is. But the idea is I keep looking at all the different connections I could write down that are compatible, but if there's a bit of torsion I can never get rid of, I'm never going to have a torsion-free one. So a torsion-free one, this intrinsic torsion has to vanish. Okay. So let me give you an example of this. And this is kind of characteristic of the first kinds of supersymmetric solutions that people wrote down, non-trivial ones. I should have said for these supersymmetric backgrounds, I sort of mentioned it. I've told you what they look like geometrically, but there's another question as to how many solutions you can find and whether solutions exist. And I want to stress that for the Calabi-Yau ones, we have this beautiful Calabi-Yau theorem that tells you that solutions exist, given certain topological constraints. And not only that, but you can work out quite a lot of the properties of those solutions without knowing the details. That doesn't happen for the G2 or the spin 7. Or actually hyperkähler. Hyperkähler is also hard. So let me do an example. So let's do the type 1. And let's do R51 times some 4-dimensional space. So I'm going to take a metric, a 10-dimensional metric that looks like the metric in 5.1, and then I'm going to have some metric on M4, and I'll take H is non-zero and phi is non-zero on the M4 space. So on this internal space, I'll let myself have some B field and some phi. So then I need to satisfy the equations that I wrote up there. So that's Levi-Civita minus a half H MNP gamma MP for some chi on, so again, I can decompose my chi into eta tensor, sorry, my epsilon into eta tensor chi, that's in 60, this is on M4. And I'll also have to satisfy the equation that gamma m, Levitch eta m, minus 1 on 24, h m n p, gamma mp minus dm phi chi is 0. Did I write that down right? Yeah. Okay. So you notice that the pair GMN chi, just as we did before, if there was no flux, this was going to be a K3 manifold, right? And it had an SU2 structure. So these things still define an SU2 structure. And so they should be equivalent to a triplet of symplectic forms, right? Because it's actually like a hyperkähler structure. And what do you find? So you find that instead of being closed, so if it was torsion-free, you would say d omega I is 0, for I is 1, 2, 3. What do you actually find? You actually find that d of e to the minus 2 phi omega I is 0. And you also find that d of e to the minus 2 phi is minus e to the minus 2 phi star in full on m of h. So solving those equations is equivalent to these equations. And if you look at these, you see that now we have d omega I is actually equal to something like 2 d phi wedge omega I. So we're getting some intrinsic torsion here, right? It's no longer 0. You get something on the right-hand side. That's some kind of intrinsic torsion. And from this equation, we get something like d phi is a half star m h. I hope. Okay. So we get some torsion here, and the torsion is related to the flux in the way that I said. So this actually, you can solve these equations. Let me keep that. So you can solve these equations. And you find the following. So you actually find that the 10-dimensional metric can be written as an R3 1-bit plus, and then actually here you can just write, where are we? You can write some e to the 2 phi, and then this actually just becomes a hyperkähler manifold. So you could see that if I sort of rescale the omegas, I could get some omegas that are closed. And that's what I'm doing. I'm doing a rescaling of the omegas so that the ones on there are closed. And then also I have the equation of motion for h, which tells me that d star h is 0. And if I take it all together, that tells me that nabla squared of e to the 2 phi has to actually be equal to 0. Where this is the nabla squared calculated for the hyperkähler manifold. Yeah. Oh, sorry, yes, this should be 5-1. So as a further example, I could just take the hyperkähler space to actually just be flat. So it could just be dx, where x is x1, x2, x3, x4. Right? I could just take it to be flat space. Flat space is a special example of a hyperkähler space. And then I could take r squared to be x squared, and then I could solve this equation, which says that e to the 2 phi actually looks something like 1 plus a on r squared. So I'm solving the Laplacian in 4 dimensions that has solutions that look like 1 on r squared. So then this solution looks something like ds squared r phi 1 plus 1 plus a on r squared dx dx. This is just the solution. So what's going on? So we've got some solution. This part just stays flat space. This part, as you go in R, right, it's got some curvature. This is just a solution around a Never-Schwarz 5-brane. It's a 5-brane because we've got a 6-dimensional world volume here. So it's like you're getting some, here's the brane, and you're getting some, there's some transverse space to the brane, which is this 4-dimensional space, and things are getting curved in the transverse space. So this is a bit like a black hole solution, right? Except instead of having just a single time direction, you have a whole brane direction. And there's no horizon, so this is a supersymmetric state. It's like the horizon has collapsed onto the singularity. Yeah. Is this, that should be 2 phi, not minus. Yes, same phi. So this is always, everywhere's the dilaton. Yeah, sorry. Oh, is that better? Yeah. Yeah. Yeah.
So I got a little bit lost with all of the phis and dilaton. So when we do that part there in the bottom left, yes, that we are looking at e to the 2.
This is the dilaton. This is the dilaton. Everything is the dilaton. Every phi is the dilaton. So this is, in fact, if I go to the near horizon limit, I'll get a linear dilaton background around there. Yep. Yes, and then, yeah.
I guess that if we have a non-zero flux on the first piece of
Yeah.
space, we cannot have flat space, right?
Right. So I just chose a very particular ansatz. So I wanted to say, let's preserve the Poincare symmetries in 6 dimensions. Then I can't have any flux on here because it would break that symmetry. Yeah. So I fixed an ansatz to make it look like the brane. Yeah. Okay, so actually each of these objects, each of these omega i's, you can build out of spinor bilinears. So if I have a solution to that, I can take, for example, omega 3 to be psi bar gamma mn, sorry, chi bar gamma mn chi, and I can take omega 1 plus I omega 2 to be chi transpose gamma mn chi. Or maybe, actually, I should write, let me just write a kind of conjugate there. Let me just write transpose. I have to work really okay. But I can build these things out of the chi's, and I know what equations the chi's satisfy. So from the equations from the chi's, I can derive these equations. Okay. So, you know, in the 90s, people found a whole load of solutions like this. Every brane that you have has a corresponding supersymmetric solution around it. And then there's a whole industry of trying to find more supersymmetric solutions with more fluxes turned on. And in general, that's a hard thing to do. So you might have enough symmetries that you can find a nice way to do it, but in general, it's difficult. So in the last bit, let me tell you a different way of thinking about the flux solutions, which allows you, what we would really like to do is to somehow think of the flux solutions as torsion-free things. That would be helpful in trying to find solutions, and it would be particularly helpful in finding moduli spaces. If I have a solution, how can I deform it? Yes? Yeah.
Do they break some of the supersymmetry? Do they preserve it?
So in general, I can ask the question of turn on some fluxes, and I can say, I want to preserve 2 supersymmetries, or I want to preserve 1 or 4. So what will happen is that this structure group will change depending on the number of supersymmetries I want to preserve. And then you'll get some constraints that that can constrain certain components of the flux to vanish. And in general, but I'll still get these relations that the intrinsic torsion gets related to the flux. Okay, so let me just say, so in general, this problem gets hard. And in particular, you actually technically don't have a global G structure. So what I mean by that, so for example, if you did type 2, you might have 2 spinners, one coming from, because there are 2 killing 2 spinners in type 2, and this one might preserve, say, an SU3 structure, and this one might preserve an SU3 structure. And so the pair of them preserve a common subgroup, which preserves an SU2 structure, but you can have places on the manifold. So in general, it's going to be an SU2 structure, but there can be places on the manifold where chi1 equals chi2, and suddenly it jumps to an SU3 structure. So you can have weird solutions where it looks like you've got 2 spinners, and so you have an SU2 structure, but actually at certain points they become parallel and suddenly you have an SU3 structure. And the whole thing about G structures was that they were global, so that doesn't make any sense, really. Okay? And then also we have, so they're not torsion-free, And this makes things like moduli spaces are hard. So typically you might want to say, I've got a solution and I want to look at how can I deform it and keep it a solution. That happens if you're doing ADS-CFT, you might have a solution, and if you deform it, that gives you a family of conformal field theories that are related by an exactly marginal deformation. And you might want to work out what that family is, but if you don't have nice equations to solve, that's very hard. If you've got equations that have 0 on the right-hand side, it's easier than if they don't have 0 on the right-hand side. Okay. So let me try and tell you a way to get around this problem. And I'm actually going to start by telling you something, and I guess I have no time, so let me tell you very quickly. So to get around this problem, so the solution for this is to reformulate the supergravity geometry. So what I'm going to do is introduce another geometry, which is going to then lead to, and then we're going to get torsion-free structures. And let's just, to keep it simple, let's look at type 2A or B, and we'll just look at the Never-Schwarz sector, which is this GMN, BMN, and phi. Okay? What are the symmetries? Well, I have diffeomorphisms, which are parameterized by some Lie derivative, and this is a vector. And I have gauge transformations, which is where delta B is d of lambda, and lambda is a 1 form. Okay? I'm going to have to be a bit heuristic. And these form an algebra. So I can do delta psi plus lambda delta psi prime plus lambda prime. And this should be some delta psi double prime plus lambda double prime. And psi double prime is just the Lie bracket between these two. That's, you know how diffeomorphisms work. And what you find is that d of lambda double prime is something like the Lie derivative of d of lambda prime minus the Lie derivative prime of d of lambda. But you'd really like to write down what d of lambda, you'd really like to write down a lambda double prime. And you can write down a lambda double prime. And the natural way to do it is you do something like the Lie derivative of lambda prime minus I psi prime d lambda. So that's slightly weird because I'm not treating lambda and double prime the same way. But if I do that, I get some mathematical structure which is called a Courant algebroid. So this defines some nice mathematical structure. So when I'm putting these gauge transformations together with diffeomorphisms, I get a natural mathematical structure called a Courant algebroid. You might like to define something symmetric. If you did something symmetric, you'd find that it wouldn't satisfy Jacobi. So you have a tension here between having a symmetric way of combining, anti-symmetric way of combining things and satisfying a Jacobi relation. This is not like a Lie algebra. It's something else. Okay? And this has a whole load of geometry, which gets called generalized geometry. And what I do is normally, so in ordinary geometry, I have the tangent space, T of M, and I have a Lie bracket. And I have connections, and I have torsion. Okay? And on this tangent space, you have an action of GLN, GLDR, right? That's what we keep talking about. That's the frame bundle. When I do the generalized thing, I have a generalized tangent space where I stick together the vectors and one forms together as a single object. So I think of this as Tm together with T star M. So a general vector here is something which has a vector bit and a one form bit. So this index now is running from 1 to 2D. And on here, there's a natural pairing where I just contract the two bits. And this thing is actually invariant under an ODD group. So there's an action of ODD on this. Just believe me. So the analog of this GLD acting here is an ODD group acting here. And there's a Courant bracket, which is exactly what I told you before. So so if I take the bracket between psi and lambda, psi prime and lambda prime, I get this psi double prime, lambda double prime, where they're defined by this relation and this relation. So it's kind of like you've got some extension of a Lie algebra. And you can introduce connections and torsion. Okay, so now I'm going to tell you some magic. So if we did Riemannian geometry, we would take a metric, and this would be invariant under OD. And OD is the maximally compact subgroup of GLD. And then we would have Levi-Civita connections, which had and vanishing torsion. And then we would have an action, which was just the curvature. So let me do the same thing in ODD geometry. So now I have something called a generalized metric. I'll call it G, because I call everything G. And this is invariant under OD times OD, which is the maximally compact subgroup of ODD. So I'm just doing the same thing. So this was an OD structure. This is an OD times OD structure in ODD. And again, I can write down a generalized Levi-Civita connection. And I can write down some, let me just say some volume form that depends on G, and some generalized Ricci tensor. Okay? It turns out that choosing this is exactly equivalent to choosing G, M, BMN, and phi. The number of degrees of freedom in this choice is exactly those degrees of freedom. And if I write down the if I expand out this action, if I work out what it is, it's the following. Which is exactly the Nevers-Schwarz sector of type 2. So there's actually a geometrical way of thinking about all these fields. You geometrize the dilaton and the B field, you put them into this generalized metric, and actually all you're doing is Einstein theory, but for this generalized thing. And in type 2, you actually get, in type 2a, for example, you get 4 different connections here. I think that stays the same. There's really 4 different connections because there's 2 different spinners. And those 4 different connections, I have this, if this is my Levi-Civita thing, this is 2D, this is 2D. So this is really, this could be in the T, this is T plus T star, this is T plus T star. So you really have 4 different connections. You sort of have a T with T, a T with T star, a T star with T, and a T star with T star. And those 4 connections are exactly these 4 connections. So these things here that look like things with torsion are actually torsion-free things in this generalized geometry. And then you can show that every supersymmetric background corresponds to a torsion-free generalized G structure for G is some subgroup of OD times OD. So by going to this bigger geometry, we've reinterpreted supersymmetric backgrounds as torsion-free things. So this is kind of bizarre, right? This is not, no one ordered this in the sense that I never put any supersymmetry in anywhere. I never talked about fermions at all. All I talked about was having a metric and a B field, and how do I put that algebra together? So in a sense, in once Einstein had done GR, you could have said to yourself, oh, Why don't I extend GR in this way? And you would have discovered the bosonic sector of supergravity without knowing anything about supergravity, right? So you can ask, but this only does it for the metric and B field and dilaton, right? If I was in 11 dimensions, what do I do then? Or what if I have the other fields of type 2, the Ramon-Ramon fields? So we had conventional geometry, and this was a GL dr subgroup. And then we had this kind of ODD geometry. So then we had, well, this generalized geometry, and this had an ODD. Technically, I lied to you. You have to also put an extra scaling factor in, some kind of conformal thing, but don't worry. Okay, I'm going to write down some Dynkin diagrams. This is the same as SLDR roughly. Let's put a plus there, times R plus. Just roughly, I have an overall scaling. That's that Dynkin diagram, right? This one is this Dynkin diagram with some number of nodes. These are Dynkin diagrams for things called simply laced groups. So there's this ADE classification of simply laced groups. That's all the roots are the same length. So all I'm trying to say is the next one you want to do is something that's associated with the exceptional groups. And you can do this as well. There's a kind of exceptional generalized geometry. It's a terrible name, right? Which is based on the group EDD times R plus. So you remember these groups were kind of what appeared in the moduli spaces for half supersymmetric. These were the groups that appeared in the moduli spaces for fully supersymmetric. So you can also do this thing, and this allows you to do this allows you to do 11-dimensional supergravity, and it also allows you to do type 2 A and B with the Ramon-Ramon fields. So you can reformulate 11-dimensional supergravity using an exceptional group. Now, what is this D? What I'm actually doing is 11-dimensional supergravity restricted to D dimensions and then reformulating that. If I wanted to do the full 11-dimensional supergravity, somehow I'd have to do E11. E11's not a Lie group. So there are some people who believe that somehow the symmetry of the full theory in M theory is something to do with E11. I think there's arguments that doesn't quite work. But if you do something much simpler, say we were looking at